Today we will be discussing about conservation of energy mainly, and the part of energy degradation is not there in the current syllabus of ICSE, so we won't be going into that part. So let us begin with the concept of the law of conservation of energy. I had already discussed briefly about law of conservation of energy in my last lecture, where I said that according to this law of conservation of energy, energy can neither be created nor it can be destroyed. It can only be converted from one form to the other. For example, when you turn on the switch of a bulb, when you turn on a bulb, the electrical energy is converted to heat and light energy. When you turn on a fan, the electrical energy is converted to mechanical energy. Okay. And this way the process goes on. Now, whenever there is some form of energy disappears, another form of energy reappears. So that is why we say that you cannot create energy, you cannot destroy energy. The sum of the total energy of the universe is a constant. Okay. So when there is a transformation of one form of energy to the other form, so as a result of which the total energy remains same or it remains conserved. Okay. Now, if we actually consider that we have an isolated system, that means a system where which does not have any interaction with the outside world, then for all types of those changes that is taking place inside the system, the total energy of the isolated system remains the same. Now, uh, conservation of mechanical energy. So since we were discussing about kinetic energy and potential energy, here we are concerned about how do we conserve mechanical energy, right? Now now in this, the conservation of mechanical energy involves uh, potential energy and kinetic energy. Now, when I say conservation of mechanical energy, I mean that the sum total of kinetic energy and potential energy of a system remains constant. Okay, provided that there are no frictional forces that are actually existing. So, whenever there is an interchange between potential energy and kinetic energy, the total energy, kinetic plus potential, that remains constant. That is K plus U is equal to constant. Okay. So this implies that whenever there is some form of loss of energy of one form, another form reappears. If there is a conversion, or if potential energy decreases, or if potential energy gets destroyed, obviously it does not get destroyed, it gets converted to kinetic energy. Okay. So if I say K plus U equal to constant, this means if K decreases, then U will increase, or if U decreases, then K will increase. So in this way, the sum total of K plus U, that always remains constant. But obviously, there must not be any frictional force which are present in this case. Now, there is a very important derivation that we have over here, where we theoretically verify this law of conservation of mechanical energy, that is K plus U equal to constant. We take this example for a freely falling body. Okay, this is the most important example that we have for verifying the law of conservation of mechanical energy. So let us consider that I have a body of mass m. Okay, so let us consider that I have a body of mass m which is falling freely under gravity from a height h which is above the ground. Okay, so if I go up and show you the diagram, this is this is the diagram. So here I have a body which has a mass m. Okay, and it is located at a height h from the ground level. Okay, U denotes potential energy, K denotes kinetic energy. small u denotes the initial velocity of the body. Okay. Small v denotes the final velocity of the body just before hitting the ground. V1 denotes the velocity of a body at an intermediate position B. So point A is the highest position of the body. Point B is situated at an intermediate position between the H, the highest position, and the ground level. And point C is located at the ground level. Okay. So let us consider that it is at a distance h from the ground. Okay. And let us consider that while the body is released from this point A, it travels a distance x. It travels a distance x before coming to B. Okay. Now, if the entire height is h and if this much is x, so this distance must be h minus x. This distance must be h minus x, right? This distance must be h minus x, right? Now, we will try to find out what is the kinetic energy and potential energy at each point. At point A, what is the kinetic energy, what is the potential energy, and we will try to find the sum total of the kinetic and the potential energy at every point and check whether the sum of kinetic and potential energy remains constant or not. That is what we are trying to do over here. Same over here and same over here. So initially, at the position A, so at position A, where the body is at a height h above the ground, initially the body is at rest, so u equal to 0 implies that kinetic energy must be equal to 0. Potential energy is maximum because it is at a height h. Okay, so it is mgh. So the potential energy of the body is mgh. So the total mechanical energy is k plus u. It is 0 plus mgh or mgh. Okay. Now we consider the next position, that is position B, when the body has fallen through a distance x distance fall koreche. In this case, let us consider that v1 be the velocity that is acquired by the body at B, right, after falling through a distance x. So initially the body is at A, at position A, and the body falls through a distance x, as you can see over here. This is A position and the body falls through a distance x to reach point B or position B. Okay, and while the body reaches position B, it acquires a velocity of v1. Okay, now after that, after falling through a distance x, let us try to find out the kinetic energy of this body and the potential energy as well, using the equations of motion. So how do we do that? So we know that the initial, if I consider that A is the beginning point of the freely falling body, then obviously u equal to 0, initial velocity of the body was 0. The distance traveled by the body up to point B is x, that is, so s equal to x, and the acceleration is nothing but the acceleration due to gravity. So from this equation of motion, that is v square equal to u square plus 2as, initial velocity was 0, so u at jayega I put 0. For in position of A I put g, and in position of s I put x, that is the displacement, and in position of v, that is final velocity, I put v1, because when the body was initially at 0 velocity, after falling through a distance x, it acquires a velocity v1. Okay, and now after acquiring a velocity v1, it has a kinetic energy which is given by half m v1 square, right? So what is v1 square? V1 square is actually equal to 2gx. So v1 square is nothing but it is 2gx. Okay, so it is half into m into 2gx. So 2 and 2 gets cancelled out, it is mgx. So mgx is the kinetic energy at position B. Now, when mgx is the kinetic energy at position B, now let us consider that what is the height of the body above the ground at position B, right? So let us find out what is the position, what is the height of the body from B. So here at position B, so position B is at a height of h minus x from the ground. So what is the potential energy? It is simply mg into h minus x, because h minus x is the vertical height of point B from the ground level. So if I add both these two, k plus u, kinetic plus potential energy, it is mgx plus mg of h minus x, which is the potential energy, and mgx is the kinetic energy. If I add these two, I get mgh. Okay, so here also I see that in the previous case at position A, the total energy was mgh, and even at position B, the total energy still remains the same, that is mgh. Now let us consider the last position, that is point C. Now at point C, that is at the ground level, let us consider that the velocity of the body just before it strikes the ground is v. Okay, now we know that the initial velocity was the body was 0, so u equal to 0. The distance traveled by the body is h. The distance traveled by the body is h, and acceleration is nothing but the acceleration due to gravity. So from this equation, v square equal to u square plus 2as. It is for a I replace with g, for s I replace it with h, and u I replace with 0. So it is v square equal to 0 plus 2gh, where v is the final velocity. So v square is equal to 2gh. I put this in the equation for kinetic energy. So kinetic energy is half mv square, or it is half m multiplied with 2gh. So 2 and 2 gets cancelled out. Again, you see it is mgh. This is the kinetic energy. And what is the potential energy? The potential energy of the body at the ground level is actually equal to 0, because we always assume that the potential energy of any body which is on the surface of the earth is 0, and the potential energy increases as the body moves away from the surface of the earth. So the total energy is k plus u mgh plus 0. Again, it is mgh. So from these three equations, it is clear that the total mechanical energy, that is sum of kinetic and potential energy for a system, remains absolutely constant. That means that, so how is it possible? When the body is absolutely at the vertical level, at the topmost level, that is position A, it has maximum potential energy and minimum, that is zero kinetic energy. When the body falls from point A, or begins to fall from position A, kinetic energy of the body slowly begins to increase from 0, and potential energy of the body begins to decrease. Why? Because the height of the body keeps on decreasing and it goes towards the ground. So while a body comes down from a height, the kinetic energy of the body continuously goes on increasing. On the other hand, the potential energy of the body continuously goes on decreasing, and at the ground level, the kinetic energy reaches a maximum value, but the potential energy becomes 0. So that means if kinetic energy decreases, potential energy increases, or if potential energy decreases, kinetic energy increases. The reverse happens when a body is thrown upwards, okay, vertically upwards under the effect of gravity. So what happens that initially the body has zero potential energy, and you say that it has some finite kinetic energy which a person supplies to it while throwing it up. So at the ground level, the body has kinetic energy but zero potential energy. While the body goes up, the kinetic energy of the body slowly goes on decreasing and the potential energy goes on increasing, because as it goes up, as it acquires height, the potential energy goes on increasing because it is mgh, but the kinetic energy goes on decreasing and becomes the kinetic energy becomes zero when the body reaches a maximum height, and at that position potential energy is maximum. Okay, so all these conversions of energy from one form to the other can be represented by a beautiful graph, which you can see it under figure 2.19, that is the conservation of mechanical energy. So this is the graph that you can see. This is the graph that you can see. So here you see in the x-axis we have plotted height above the ground, and on the y-axis I have plotted energy. Now as the height above the ground goes on increasing, the potential energy increases, and the kinetic energy at the ground level is almost maximum, which is equal to mgh. So if potential energy increases, kinetic energy decreases, and at an intermediate level, that is h by 2, kinetic energy and potential energy are almost the same. And then at a maximum height h, potential energy is maximum but kinetic energy reduces to zero. So this is a very, very important graph which is important from the exam point of view. So here from this table you can understand obviously how the body behaves under at different positions or at different heights, at point A, at point B, and at the ground level. Okay. Now, although this thing is not there, the application of this law of conservation of energy to a simple pendulum, I just want to discuss it qualitatively as to what actually happens. Simple. I'm just focusing on the diagram which is over here. Now in the diagram you can see that there is a simple pendulum consists of an inextensible string and a bob, right? Now at the mean position, that is at this position, at position A, the bob is at its rest position, right? Now if the bob is moved like this, it will oscillate in this fashion, right? So if you move the bob, it will oscillate. When the bob reaches this point C or point B, these positions are called the extreme positions. So when the bob from A goes to point B, the potential energy of the bob is maximum because it is at a height from with respect to this point A. We consider that at point A, the potential energy of the body is zero. So if potential energy is zero, then kinetic energy is maximum. So while it goes up, it goes against the force of gravity. So kinetic energy decreases and becomes zero at the maximum point B. And at that position, potential energy reaches a maximum value, that is mgh. From that position, the bob again tries to come back to its initial position. And while it comes to point A, due to inertia of motion, the bob does not stop, but it goes on moving. When the body reaches this point A, it has minimum potential energy but maximum kinetic energy. Again, when it goes to C, it reaches another extreme position. Over there, the potential energy of the body is maximum, but the kinetic energy reaches almost zero. Okay, so this is a practical example of the law of conservation of energy with respect to a simple pendulum. Okay, so thank you for listening to this lecture. Thank you.